We have finished with spline interpolation, the integration online quizzes, and I do appreciate people being proactive about scheduling your one-to-one meetings. They've been very productive, and I'll be looking forward to talking with the people this week. So the next topic is, well, integration is there, and according to the usual pattern, we now have a programming assignment. This is x cubed plus 2. All right, so let's make it very clear. If we're going to show everybody, we can put parentheses there so that it looks nicer. Whoops. All right, there we go. Okay, compute the exact integral by hand. Okay, hopefully that's not too difficult. Okay, estimate the integral using trapezoid method for these different sizes, these different values of h, or values of n, sorry. All right, so of course when n equals 1, you're going to use the entire interval and just one trapezoid, 2 trapezoids for n equal 2, 4 trapezoids, etc. Okay, so make a plot that includes the following. I don't know why it's doing that. It should join automatically. Right, but I guess I have to be in Google Meet to make it join automatically. All right, so make a plot. So these plots are supposed to show some aspects of convergence. You see here that we're doing the same integral with different n. Of course, with different n, larger n means smaller h. Smaller h, just like with derivatives, smaller h means more accurate approximation. So here we're seeing what the effect of n is on the accuracy of the integral. So make a plot that includes the log of the absolute error on the y-axis versus the log of the number of trapezoids. Okay, so make this a solid line. Now, I suppose you can either do a log-log plot of the values or actually plot the logarithms versus each other. Just do what looks best. They should look the same, but the scales will be different. Okay. So you do have those two choices. Either do log scale on x and on y, or actually plot the logarithms versus each other. So this is log of absolute approximate error. Okay. So this is approximate error, not the... So make sure you've got the difference between approximate error and absolute error. So this is, maybe I should make this clear, this is the log of the absolute true error, just so you make sure that you distinguish between the two. Right. Now you can compute the true error because of course you can compute the integral exactly. But approximate error, remember that means the difference between successive terms. Okay. And this plot includes all of these together. Right. So it may be a little bit crowded. Well, I suspect that these higher ones are going to kind of, well, we'll see. All right. So yeah, there's going to be a bunch of stuff here. It may be too crowded, but that's all right. See how it works out. So log of absolute error versus the approximate error versus log of number of trapezoids. Okay. So make this a dotted line, okay. Or make this dotted lines. Okay. So these are going to be no, I'm sorry. This is not several lines. This will be a single line, right? Because you have a single line for all these. Oh, wait a minute. So yeah. This will be a single line. This will be a single dotted line. So it's not going to be too crowded. Okay. So this line will begin at n equal 2. Of course, because you can't get an approximation for the first estimate because you don't have another previous estimate to compare it to. And I didn't close my parentheses. I always forget to do that. All right, so, and then the D goes wrong, so let's see. I have to do space. There we go. All right, then you've got this, okay. Okay, then it says calculate the slopes of the lines you obtained in C. All right, you've got two different lines, and you want to explain this result in terms of the theory. Okay, so we had so remember in the differentiation of continuous functions chapter, you did get slopes. For forward difference, the slope was 1. For backward difference, also slope was 1. And for center difference, the slope was 2. And that was very significant because the slope of 2 meant the convergence was faster, and the rate of convergence was like the square of delta x. So the arrow went down as the square of delta x for centered, and the arrow went down as delta x for the forward or backward. So I think the person joined already. So let's see. So several comments on coding. Define your integral as a function. Okay. So this way, define the integrand as a function. Okay, this way it's extremely easy to use the same code for a different function. Okay. Now, of course, you also have to define the exact value of the integral, and that will be a number. Now, I've been emphasizing to people in your codes, after you initialize, there should be no specific numbers or functions in the code. You want to write your code so that it will work not just for the given function, but if I decided to put in another function, it would still work. Okay? So define your trapezoid algorithm also as a function, and that will be handy because you'll be using the same function for other parts of the problem. Right. Like in part 2. Okay? The function's inputs will be the function to integrate, the two limits, and the number of trapezoids. Right. Now, also want to emphasize that when you write a function, inside the function, the only variables you should use are the ones that are passed as arguments. All right. So, for instance, if you need, this gives you the number of trapezoids here. So, if you need something, you should calculate it from the inputs. Right. Now, for the because you're actually passing in the function to integrate as an argument. Okay. So the function's outputs will be the estimate of the integral. So there's only one output. Do not use any loops inside the trapezoid function. Use vector operations instead of loops. Right. So I'm wanting to get you into using NumPy arrays. And I think I've said before that you should use NumPy arrays instead of lists whenever possible. I don't know, apparently when ChatGPT gives code, it likes to use lists, but that's not the way to... When you ask ChatGPT, you should specify NumPy, and then it will do things with NumPy. And people have used math and C math and other things like that, but I prefer just to use NumPy because it's basically a all-purpose tool. Okay, so make your plotting routine to be a function also. Okay, the inputs will be a list of the functions to plot, the title of the plot, Okay, now I guess what you'll also have to have, here, this should be it. I guess you'll also have to have, no, that's fine. That should be fine. So the function will have no return value, but will produce the plot. Okay, so make the slope calculation also a function. Inputs would be the vectors, x and y values that you're fitting the line for. Output would be the calculated slope. Now, when you did a derivative, there were several ways to calculate the slope. Some people used, I think most people used 2 consecutive points. I think the rule is if you use consecutive points, you should use 2 of the later points, not the earlier points. Another way to find a line is typically if you want to find a line with a bunch of points and the line has some noise in it. Let's see, I think my tablet's all set up here. Okay, yeah, we're good. So if you want to find a line, and you have some noisy points, like this, something like that. If you choose 2 consecutive points, then there's bound to be some error. It's good to choose an earlier point and a later point like this, and then the error sort of averages out. But the very earliest points have more error. So a good strategy might be choose some point sort of in the middle and then the last point. You might try some different possibilities and see what you get. See if they agree well. And quite likely the result should be an integer or close to an integer. Maybe not, but we'll see. Okay. All right, so the output would be the calculated slope. So you call this function twice, once for the true error and once for the approximate error. All right, so we've got the same thing for this integral, and then repeat all the 4 parts. Okay. Okay. So the 2 should be a piece of cake if you did 1 correctly. It should be almost nothing. Right, so this is just to check. I suppose this exercise is sort of to check on whether you did the coding for part 1 well or not. Okay, so and then 3. Also, this will be almost nothing if you do part 1 correctly, because you're doing the same thing just using Simpson's rule. Now, but in this case, in your 2 parts for plot C, do the trapezoid rule and Simpson's result on the same axes. And note you won't be able to do the 1 segment method with Simpsons. That's okay, you'll just have 1 fewer point. And as in 2, make use of the functions you defined in 1. All right, so you can see that we're building up our code to be more and more elaborate. So we covered trapezoid rule, we've covered Simpson's rule, and then here is Richardson extrapolation. So you know Richardson extrapolation is the method that's used for Romberg integration. So if you finish the reading, you'll know what I'm talking about. Basically, that what Richardson extrapolation will do for trapezoid rules, it takes pairs of trapezoid rules and it extrapolates. And just to go over, well, maybe I'll go over briefly in the write-up what Richardson extrapolation does. It's a very nice technique, and it doesn't just work for integrals. Same sort of thing will work. If you know the dependence of the error on your parameter, you can use 2 estimates to get a better estimate. And this is also used in differential equations and I think other applications as well. Right. So with trapezoid rule, you compute the 1st, 2nd, 3rd, 4th, 5th best approximation. And in the book, this is I21, I22, I23, I24, and I25. So make use of the functions you define in 1. There's no graph in these exercises, just output the 5 numbers. Okay. All right, so then write code to give a 5th order Romberg. So this builds on this one because these estimates give you, then you go to the next level and the next level and the next level. Right. Okay. Then number 6, copy and modify your code from 5 so it can find Romberg approximation for the integral for the given function on a given interval to a given order. Actually, if you write your code for 4 well, or write your code for 5 well, then this should be easy. In fact, if you write your code for 5 well, then 6 will be done automatically. Because you should write your codes so that all you need to do is replace the function definition, and it will still work. So 5 and 6 really go together. All right, so let's go over the let's go over the text briefly. I don't think I need to go over let's see, it should be under, no, I thought, well, here, we'll just find it. I'll just look for integration. By the way, if you don't have this software, this is free software that enables you to find anything on your hard drive very easily. And I use it all the time. If you just Google everything, you'll find it. The name of the company is Void Tools, and very, very handy. You can tell what you're searching for. I know I'm searching for a document, so I can click Document, and I just type in, I think, integration, and I may not be able to find it. And then let's see. Let me order it by size, because it should be relatively large. Yeah, it's not here. So I may have to pull it off the web. Let me look one other place. I believe that my folder name is English. Yeah, it should be here. Yeah, that's exactly where I thought it was, but I didn't see it. And then I can click on this and go in. So here we go. So there should be integration here somewhere, because I thought I had everything here. Anybody see it? I do not see it, but it should be here. Oh, Romberg. Here we go. Okay. Yeah, so Romberg includes the discussion of what's it called? All right, so we'll skip through this. You know what an integral is. All right, so here, first of all, he's computing the dependence of the trapezoid rule error on the number of trapezoids, or on h, which is the same thing. I mean, h is going to be proportional to 1 over n. So he goes through this and uses our old friend Taylor series. So this error estimate, it's familiar, comes from Taylor series. I believe that this error was derived in the trapezoid rule section. So the error is proportional to 1 over n squared. So this is the basis of Richardson extrapolation, that you know that the error is proportional to 1 over n squared. So the idea is that you can, if you take two equations and you know the error of both of them, then you can eliminate the error from the equation. All right, so let's go on here. All right, so here he does an exact integral, which is kind of messy. Looks like he's doing approximate error, but the true error is, all right, so yeah, so you can see it goes down by a quarter each time, and in fact that should become more and more accurate as you go along. All right, so Richardson extrapolation says, okay, so I know the n-segment trapezoid rule has an error of some constant, and this constant is related to the second derivative. It's the same constant for every n, and that's key. If it was a different constant for different n's, the method wouldn't work. Now, of course, this is an approximate expression for the error, because you know Taylor's series is infinite, and this is just the first non-zero term in the Taylor series. But it's a pretty good approximation. So let's go with that. So the error is the true value minus the approximate value. So if we have two different errors, whoops, sorry. If we have two different errors, right, this is the c over n squared, that's the error for n intervals. Then if I double the intervals, I'm going to get c over 2n squared. All right. Now, so what you got here is two equations. And what you want is TV. Okay. So, and you know in and I2n. And you know n and n squared. You don't know c. All right. So you can use these two equations to eliminate the c, right, and solve for TV. And if this were an exact equality, that would give us the true value exactly. But as it is, what it does is it eliminates the second order error. And the only error that's remaining is higher order error. Okay. So when you eliminate the c from the equation, this is what you get. Okay, so this is the I2n, and then this is the correction term. Right, so he does an example. Right. And there's Richardson extrapolation. And then he goes to town on this. He said, well, this works for trapezoid rule, so why not do it again? I mean, it's like the kid. When he does something, then he likes it, he'll apply it to everything. Okay? Mathematicians are like kids. So this was trapezoid rule, and when you did this, and you got let's see. Let's see. Now we have here. All right. Now, so the exact error is here. So once you use trapezoid rule, you basically eliminated the first error term. Right, so we want to look at the next error term. Can we eliminate the next error term? Well, if we now have error terms that have this order of the error is proportional to h to the fourth, we can do the same thing with two different Romberg terms, because we know that the error depends on h in this way. Okay. So we can set up pairs of equations. So I should say that up here, we didn't just get one estimate, because here we have several trapezoid rule estimates. So for each successive pair of estimates, I can get another better approximation. So out of these 8 original values of n, I can get 7 Romberg estimates that have less error, because I'm taking the difference of successive ones. And I know the error of approximation is not n squared anymore, it's n to the fourth. So then I apply the same old rule, but with n to the fourth now. Well, with h to the fourth, sorry, I said n to the fourth. Let's see. All right, so this is the equation we had before. This is the equation we had before, and this 3 came from this power of 4. Oops, sorry, I skipped up. Can I do this? Sorry. Okay. Let's see over here. So if you use if you take the result of Richardson extrapolation applied to trapezoid, your error term is no longer ch squared, it's ch to the 4th. And if you take two successive approximations and you solve and you remove the error as before, you get something like this. And notice the difference here is only in the denominator here. Instead of 4 to the 2 minus 1, it's 4 to the 3 minus 1. And you just keep on going with this. You just repeat it ad nauseum. And I think that he has some example here. Okay. So this is the way it's going to work. Here, you're using 1, 2, 4, and 8 segment trapezoid rule. So let's see, how does this work? All right. So that's 1, 2, 3, 4. There are 4 values. So the I11 was computed using the 1 segment. The I12 was with 2 segments. I13 was with 4 segments. And I14 was with 8 segments. Then we're going to use these 4 estimates to get 3 higher order estimates. I21, I22, and I23. Now I have 3 higher order estimates. I'm going to use this to get 2 third order estimates. First I'm going to use the first 2 and then the second 2. And then I'm going to get 1 fourth order estimate. And that, of course, is the most accurate estimate I've got. So this just shows the dependence. Now you see some of these values turn out to be exact, but that's just lucky. It might not be that way in another integral. But the last value is definitely going to be more estimate. So each time you go up by 2, so this one has order, error is order h squared, this one has order h to the 4th, this one has order h to the 6th, this one has order h to the 8th power. That's extremely accurate. So for instance, if your h was 0.1, then, and 0.1 is not such a small number, then your error would be 0.1 to the 8th power, which is extremely small. So you can even get away with a fairly large step size, like 0.25. All right. So when you're doing this coding, you can follow, of course you do want to follow the examples that they have here. And you can probably, you will certainly need a loop to do the different orders of Romberg. Right? If you're doing, for instance, if you have, in this case where you have 4 values of trapezoid rule, you're certainly going to need a loop to get the orders from 4 to 3 to 2 to 1. But within that loop, you should not need another loop. That should not be necessary. All right, that's all I have to say. I hope you're still there. If not, the recording is here. Anybody there?
Yeah, we're here.
Oh, all right, wonderful. Okay. All right, questions? Let me pause the recording.